Every telescope points outward, sees nearly the same sky. That uniform view tells us something deep about the cosmos. In this video, I explain why the universe looks the same. The short answer is cosmic homogeneity and isotropy. Homogeneity means matter averages the same, everywhere on large scales. Isotropy means the universe looks the same in every direction. Those two ideas form the cosmological principle, a working assumption. But it's not empty philosophy, it's backed by measurements and predictions. Stick around and you will see what we observe and why. Look up at the microwave sky, it's terrifyingly smooth. The cosmic microwave background is radiation from the early universe. We measure its temperature across the sky to high precision. The temperature varies by only 1 part in 100,000. That tiny variation is what later became galaxies and stars. Why was the early universe so uniform, across vast distances? This matters because uniform initial conditions set the stage for structure. Photons separated from matter roughly 300,000 years after. That radiation has traveled nearly unchanged until it reached our telescopes. Satellite maps like COBE, WMAP, and Planck show the uniform sky clearly. Example in real terms, the CMB temperature is about 2.7 Kelvin. And fluctuations are around 10 to the minus 5 relative to that number. Those measurements anchor the idea that the universe is isotropic on large scales. Quick mental image, a nearly uniform fog with tiny ripples across it. Those ripples seeded everything we see billions of years later. So the cosmic microwave background gives concrete evidence for isotropy and homogeneity. And importantly, it measures conditions over the entire observable sky, not one spot. Recap: the CMB's tiny uniformity explains why the universe appears the same. Look at maps of galaxies, they form webs and filaments across space. Yet when averaged over vast volumes, the distribution evens out remarkably. Homogeneity means no special place in space on large scales. This matters because cosmological models assume uniformity to simplify equations. Surveys like SDSS and DES map millions of galaxies in 3 dimensions. They measure positions and redshifts, giving a volumetric census of matter. Mechanically, we bend space into cubes and count galaxies per cube. As the cube size grows, fluctuations shrink towards the average density. Example with numbers at scales of about 100 megaparsecs, uniformity emerges. 100 megaparsecs is roughly 300 million light-years across. At that scale, galaxy counts per volume vary by only a few percent. So even though locally the universe looks clumpy, overall it smooths out. That observation supports the cosmological principle used in theoretical models. Quick tests split the sky into opposite hemispheres and compare densities. Surveys generally find no significant large hemispherical asymmetry above statistical noise. So galaxy mapping gives concrete evidence for homogeneity on huge scales, and these maps connect directly to the tiny fluctuations seen in the CMB. Recap: galaxy surveys show the universe evens out when viewed broadly. Think about causality: distant regions couldn't exchange signals early on, yet they show the same temperature in the CMB, puzzlingly similar. This is the horizon problem, a core cosmology puzzle. Inflation offers a mechanism that stretches tiny regions into cosmic scales. It happened a tiny fraction of a second after the Big Bang. During inflation, space expanded faster than light could bridge regions. That expansion made causally connected patches share the same conditions. When expansion slowed, those patches appeared separated across the sky. Mechanically, inflation smooths curvature and dilutes irregularities rapidly. Example number: inflation can expand space by about 10 to the power of 26. That stretch takes microscopic quantum fluctuations to astronomical sizes. Those fluctuations become the seeds for the CMB ripples and galaxies. Inflation also predicts a nearly scale invariant spectrum of perturbations. Measurements match this prediction, strengthening inflation as the likely explanation. So inflation explains why regions that never touched appear the same. Without inflation, the uniform CMB would be a deep mystery. Recap: inflation stretches tiny patches into large, uniform regions across space. Think about light travel: we only see out to a finite distance. The universe has an age, about 13.8 billion years. That age limits how far light could have traveled to reach us. So our observations form a spherical observable universe around Earth. Within that sphere, isotropy means no preferred direction in our sky. This matters because different observers see different observable spheres. Yet the cosmological principle implies any observer sees similar large-scale statistics. Mechanically, light from distant regions integrates conditions from the past. So isotropy of the observable universe reflects averaged past conditions. Each direction samples different distances, yet similar statistics appear. Example with numbers, the observable radius is about 46 billion light-years. That radius exceeds the universe's age times light speed due to expansion. Our observable spheres from two distant observers overlap significantly, sharing information. This shared information helps make isotropy consistent across places and times. The instruments we use detect photons from many different epochs and distances. Overlaid data reveal temperature maps that confirm symmetry on large scales. So finite light travel and expansion shape what we observe as isotropic today. Recap: the observable universe is limited, yet appears isotropic for clear reasons. Numbers matter. Cosmologists use statistics rather than single measurements. We never expect perfect equality, only statistical sameness across directions. Cosmic variance describes the inevitable sample noise from observing one universe. This matters because small deviations can simply be chance, not new physics. Mechanically, we compare power spectra from different sky patches to quantify variance. Power spectra compress fluctuation strength as a function of angular scale. Example number: the CMB power at large angles has larger cosmic variance. That means big features on huge angular scales are noisy measurements. So a mild hemispherical asymmetry may be statistical, not a violation. We test significance by computing p-values and running simulations. Simulations generate many mock skies, sampling cosmic variance effects directly. If observed anomalies are common in mocks, they are not surprising. On the other hand, rare features warrant new physics or better understanding. Quick mental image: tossing coins is like sampling cosmic variance every trial. One coin may show 10 heads, but many coins average to 50%. Similarly, the universe allows fluctuations, yet its large-scale average remains uniform. So statistical tools let us separate chance from genuine anomalies effectively. Recap: cosmic variance means perfect isotropy is unnecessary for cosmology to hold. See the small ripples, they are not errors but essential features. Tiny temperature differences in the CMB trace density variations in the early universe. Those variations grew by gravity, forming galaxies and clusters over time. This matters because without anisotropy, structure could never form. Mechanically, overdense regions attract more matter, amplifying the contrast slowly. Dark matter plays a key role, collapsing first, then dragging gas along. Example: fluctuations of 10 to the -5 existed in the CMB. Those tiny contrasts grew and formed galaxies after many billions of years. We observe anisotropies on small scales, like galaxy clusters and voids. But their existence is consistent with an overall homogeneous universe at large scales. Tiny anisotropies also inform us about the universe's contents and laws. They let us measure dark matter density, baryon fraction, and expansion rate precisely. Quick mental image: tiny hills and valleys in a cosmic landscape growing larger. Simulations starting from these anisotropies reproduce the cosmic web remarkably well. So anisotropy is not a contradiction, it's the reason the universe is structured. Observationally, we quantify anisotropy amplitude and compare it to theoretical predictions. When numbers line up, our models gain confidence and predictive power. Recap: tiny anisotropies seeded complexity while preserving large-scale sameness. Consider why isotropy matters beyond curiosity and neat math. It constrains the equations that describe the universe's expansion and fate. Homogeneity simplifies Einstein's equations, making cosmological solutions tractable. This matters because deviations would imply new physics or exotic matter forms. Dark energy's properties are inferred assuming isotropy and homogeneity hold. If the universe were anisotropic on large scales, our distance measures would shift. That would change inferred dark energy density and cosmic acceleration history. Mechanically, we cross-check isotropy by comparing supernova distances in all directions. Example: thousands of type Ia supernovae inform the expansion rate across the sky. So far, those measurements align with isotropic expansion within uncertainties. Large anisotropies would also affect cosmic microwave background polarization patterns. Future experiments will probe polarization with greater sensitivity and detail. Detecting a real large-scale anisotropy would revolutionize cosmology overnight. It could hint at exotic early universe processes or unexpected fields. But current evidence supports the cosmological principle strongly and consistently. That support underpins our confidence in models of dark matter and dark energy, so the apparent sameness of the sky is central to modern cosmology success. Recap: isotropy simplifies theory, constrains cosmology, and guides future experiments. We started with a surprising fact that the sky looks the same. Now you know the basic reasons why that apparent sameness occurs. Cosmic inflation, the CMB's uniformity, and large-scale averaging all contribute. At the same time, tiny ripples seeded all the structure we see today. So the universe is uniform and beautifully complex at once. If you enjoyed this, consider subscribing for more calm cosmic explanations. Thanks for watching. I hope the universe feels a little less mysterious.